Welcome back to Stats with Warnke. Thank you for taking on the challenge of AP Stats with us today. Today, we'll be covering the locations of means and medians in density curves. We'll also be introducing the idea of density curves. And then we'll be introducing normal distribution. So all the stuff we're covering today is kind of foundational for where we are going to be headed this chapter. And in general, we're going to be headed throughout AP Stats. So first, let's look back a little bit at what we've been doing. So we've been looking at distributions of quantitative data. And when we do that, we make a graph. So we make a box plot, we'll make a histogram, make a stem and leaf plot, things along those lines. So then once we have that graph, we can then talk about the center, shape, unusual features, and the spread of all of that. And then from there, we can calculate our summaries and kind of describe it more fully. What we're going to be talking about today is that same type of idea of describing data, but we're going to kind of replace the histogram or replace a box plot or things of that nature with just one line. It's one curve. And that curve is going to give us a pretty good idea of what everything looks like in terms of shape, and it's going to kind of iron out some of the irregularities. So a lot of the unusual features we'll just kind of either ignore or just kind of quantify them in a little different sense. So here's an example of what we're looking at. We're going to be talking about density curves. And here is a histogram of ITBS scores from Gary, Indiana. So there's about 1,000 of those scores. And as you can see, it's approximately symmetric. And we have a curve, the red curve, kind of outlining where the histogram lines up. So we have about the same median. We have the tails going down to the lowest values, and they're about the same. But what you'll notice, there are also some gaps. We have some places where the curve underestimates and overestimates the histogram. And what you can think about is if we just kind of cut off those pieces and were to move them around just a little bit, it would kind of fill in that area under the curve. When we talk about our percentiles, like we did in the first section in this chapter too, we know that we're talking about out of 100%. So our density curves has an area underneath of it of 1. And to kind of help account for that, we're going to make sure that it's always positive. So we're going to keep it above the horizontal axis. When you think about a density curve, really we're thinking about shape. So it gives us a really clear picture of what the shape of the data is. When we're also thinking about density curves, we can think about where would the mean and the median be. So again, we can locate the centers just by kind of looking at what the shape might be. So in the first example on the left-hand side, that has a normal distribution, has a very symmetric shape to it. We have a mean and a median that are in the exact same location. Whereas in the graph on the right, that has a skew to it. So as that skew to the right side, pulls the mean in that direction, pulls it towards the tail. And so that's what we can talk about mean and median of density curves. The median is the same as it was when we had any other of our graphs. It's that exact balance, it's that exact middle. Whereas our mean is the balancing point. So you can imagine if you were going to put your hand underneath of it, where would you need to put it in order to get that the balance? And so it's going to pull it a little bit in the direction of the mean. It's not going to be super far away from the median unless you have a really strong skew, but it's going to pull it in the direction of that tail. Density curves are idealized versions of our data. So going back to that histogram, we had the overestimates and underestimates by that curve. That's the same idea. We are idealizing the data to say, yes, it's perfectly symmetric. We're going to distinguish our normal curve or density curve from our typical data, just that sample that we took, or in that case we had the 947 students, by labeling our mean and our standard deviation a little differently. So we had been labeling our mean x bar, and we use that whenever we have a sample mean, and we use s sub x when that is our sample standard deviation or the actual observations. When we're talking about an entire population, or more often kind of the generalized, like this is the approximation of that, we're going to use the Greek letters. So we're going to use mu and sigma, mu being the mean and sigma being the standard deviation. Again, those are approximations. So when we go through this chapter, we're going to start using the words about and approximately just about every single problem. The reason for that is because we want to say that this is what the number likely is, but it's not exactly this. It's going to be in this neighborhood. So here is what our normal curves look like. Normal curves are a special type of density curves, and they have a couple unique features to them. So the first is that the mean is in the center. They are exactly symmetric. They are beautifully symmetric. Another feature of them is that the standard deviation is the distance from the center to the inflection point. So if you've taken some calculus, that'll make a little bit more sense. But you kind of think of it as where the slope of the curve changes a little bit. And so it goes from being that steep slope to a little more gradual slope. That's a unique thing about our normal curves. Also, one thing about them is they can have these two different shapes. We have not just one specific normal curve, we kind of have a family of normal curves. So this one's a little bit, on the left is a little bit flatter, has a little bit more area in the tails, whereas the one on the right-hand side, that one's more narrow. So it has a lot of values close to the mean, and then it has a very small standard deviation. Our book will sometimes abbreviate it as N parenthesis and then mean and standard deviation. I'll give you those pieces of information in that format. That's not something that is kind of standard across all of AP statistics. And what I mean by that is it's not something you're going to see on the AP exam, but it's something that our book uses. So I just wanted to make you aware of it. When you see that notation, they're talking about a normal curve and they're giving you the mean and the standard deviation. So what makes these important, or what makes them relevant to us, is that normal distributions are, number one, kind of make math a little bit easier, make a little of the assumptions a little more standard. And they also do a really good job of describing data sets. So we're not going to say that this is exactly true, but we can say that it's in general follows this pattern. So some places you might be familiar with that is like scores on standardized tests. We kind of normalize those, or on kind of any type of test, intelligence tests, or different assessments. You also might see it on things that are manufactured. So for example, if we have two containers, we have a bowl and a lid that goes on that bowl. We want those to be able to fit. There's going to be some variation just due to manufacturing differences. Sometimes the materials are going to be a little different. Sometimes the environment that it's made in might be a little warmer, a little cooler, and so that'll affect the manufacturing process. And so we have a range where the mean is the specific one we're aiming for, and then the standard deviation due to those variations in manufacturing processes. And also some characteristics of biological populations. So for example, height. We have a mean height. You're going to have some people who are a little bit away from that, but the farther you go away from that mean on both directions, getting shorter and taller, you're going to have fewer and fewer. So normal distributions are good approximations of the results of probability events. So when we get into probability in chapter 5, we'll also be using normal distributions and different density curves of that nature. And also, when we get into statistical inference in AP Stats, a lot of this is kind of algebra based. And so we'll be doing a lot with normal distributions. There are a couple other types of distributions that we'll be dealing with as well, but we'll get into those when it's time. Just a quick reminder, again, I'm emphasizing it a lot because this is a very commonly missed thing on both the test in class and on the AP exam. We use the words about and approximately liberally because these are just models. These are not the exact information, so we're never going to say with 100% certainty that this is the answer. We're going to say it's about this, or it's approximately this value, because we're saying that the model we used could be a little different than what it actually is. So here is our normal curve for standard deviation, for z-scores. So along that x-axis, you'll see z-scores. So that is how many standard deviations we are away from the mean. So we have a rule that applies to normal curves, and that rule is the 68, 95, 99.7 rule. As you move away from the mean, there are specific intervals that are very close to nice percentages. So approximately 68% are within that one standard deviation away from the mean. So if you go up one standard deviation, below one standard deviation, the values in between that are about 68% of our data. If you move out to 2 standard deviations, you include about 95%. Again, these are about or approximately values. We can actually calculate them, and they'll be a little off. They might be like 67.98 or something in that nature, but we can say it's about 68 and about 95 and about 99.7. So those are our 3 rules for approximating data quickly. When we want to find something at a specific defined boundary, 1 standard deviation away, 2 standard deviations below, 3 standard deviations above, or greater. So for some simple arithmetic, real quick, if we have this is 68 within 1 standard deviation, what we can also look at is how much might be in this tail. Well, if we know this is 68 in the center here, and the total area is 100%, we can subtract those, and we end up with 32%. So we have 2 tails, so we divide by 2, and we get that each tail should have 16% of the data. If we move up to 2 standard deviations, we can do that same process. We do 100% minus 95%, and we get 5% should be in those 2 tails, and then we can divide by 2, and we get the area in those is 2.5%. Same thing applies to 99.7 when we move to 3 standard deviations out. Those 2 tails should have a total area of 0.3. So when we divide by 2, we get each of those tails individually has a 0.15% of our observations. Not very significant, but sometimes that's what we're interested in, is those extreme values. When we do problems, we're going to be talking about the proportion of observations that meet or exceed a specific criteria, and we're also going to be talking about the probability of some event meets that criteria. So what we are using, the percents that we're going to be coming up with, are either a proportion of observations that meet something or exceed it, or the probability that something occurs. You can kind of interpret it either ways, and that would be correct. Also, when we're doing these problems, you're basically going to take the question, chop off the front part, the what, and then replace that with your answer. So this is going to be a little bit easier than some of the problems we've done in the past, because you don't have to create a response in as much detail. They kind of give you the formatting, you just have to insert your work. So whenever you do these problems, you should start by sketching our distribution. So start by sketching our curve, shading in the area that is appropriate for what we are interested in, and then marking any boundary values and showing any work that you do. You can do work on the calculator, and in the future I'll show you kind of how our calculator can do all this. But for right now, just write down the simple arithmetic. Show the steps that you're typing into your calculator. So here are 2 graphs. They are the same information, it's just that one on the left is a histogram, and the one on the right is the density curve of that same histogram. So we're taking those kind of bars, chopping off the ends, and filling in that curve. So this is batting average for some MLB players. So the next problem is going to be referencing the same idea. It says in the previous example about batting averages for Major League Baseball players, the mean of the 432 batting averages was 0.261 with a standard deviation of 0.034. So then they go on to tell you that that's our mean and our standard deviation. They just include that with the Greek letters because these are approximations. We took those curves and we approximated that histogram. So for A, it says sketch a normal density curve for this distribution of batting averages and label the points that are 1, 2, and 3 standard deviations from the mean. So go ahead, pause the video, and sketch your curve. It'll probably look something like this. So we have our curve that is centered at 0.261, and then we go up 1 standard deviation by adding that 0.034. Whenever you do a normal curve, it's good to label the mean and the standard deviation. You don't typically have to write out all of these values, although you should always include context. But you should label these as needed. Just include the mean and the standard deviation, and then any boundaries that we are interested in. But for right now, it's just some good practice with drawing a normal curve. So let's move on to the next problems. For question B, it says, what percent of the batting averages are above 0.329? Show your work. So the first thing you should do is start by sketching a curve. Here is a curve that I've graphed. What we can do is, because this is a nice standard deviation away from our mean, is do some simple arithmetic and calculate what is the probability inside that tail. So we start with 100%, and we subtract 95 because that is 2 standard deviations away from the mean. So we can use our rule of 68, 95, 99.7, and because that's 2 standard deviations above, we use 95. Since we're only interested in that one tail, we'll divide by 2 and we get 0.025, or about 2.5%. So that's our answer in context. And here's a little bit more description of what that's talking about. Feel free to take your time, pause the video if you need to, and go over those. Here's question C. What percent of batting averages are between 0.193 and 0.295? Show your work. So again, start by graphing this. So draw a normal distribution, label the mean and standard deviation, and the boundary values that we are interested in. It should look something like that. So we start by labeling that mean, and then you can label the values of interest. You'll notice here we have that 0.295, and over here we have the 0.13. Well, what we can start with is we know that within 1 standard deviation, so this value right here, that's going to give us 68%. So we're going to start with 68%. Just kind of park that off to the side for the moment. Then what we'll do is we will calculate what is that remaining tail. Well, what I know is that outside of our 68%, that there's 32% of the values on the sides. And since this is only one side of that, we divide by 2, and we get 16%. So I'm going to park that number right there for a moment. Then if I move to 2 standard deviations away, like this is the 0.193, that tail is, both tails combined is 5%, so we divide by 2 and we get 2.5%. So I'm going to subtract that from 16 and then add that together with 68. And just by doing that simple arithmetic, we end up with 81.5%. About 81.5% of batting averages will be between 0.139 and 0.295. The stuff in green here is what you would need to put into your notes. The stuff in black is just kind of that description of how we arrive at those answers. Thank you for joining me tonight. As always, feel free to let me know in class tomorrow if you have any questions. Thank you for taking on the challenge of AP Stats with us today.